to introduce Fiaz Ahmed. And I first became aware of Fiaz's work when he was looking at water vapor precipitation relationships for convective and stratiform rainfall. And apparently that work came out of going to, in the field, to the Dynamo Field campaign, which some of you may have heard about. And that was the first thing that Fiaz did in graduate school. And he was actually still on the Maldives when there was a military coup. So you can ask him questions about that. Kind of a fun story, and I guess apparently Angel was there as well during this military coup.
Yeah, you should ask Angel. It's a lot more fun hearing her.
So Fiaz got his PhD from Texas A&M, working with Courtney Schumacher, and partially he looked at these kind of water vapor precipitation relationships, and then he met David Nealon at UCLA, who suggested that he delve more into thinking about those with respect to buoyancy as opposed to just moisture. And so he did a postdoc and then has had various positions associated with UCLA since then. And he's done lots of work related to convection and convection impacts on climate and weather. And he's going to tell us about a lot of that work. So yeah.
Thanks, Larissa. Yes, so Larissa said I'm interested in tropical convection.
Did you unmute the mic?
Is that better?
Yes.
All right. So I'm also interested in large-scale dynamics within the tropics. And this talk, I'll touch upon both aspects of small-scale tropical convection and ITCZ dynamics. So a long list of collaborators, Sachin Dewan and David Nealon at UCLA, Kathleen Skiro, Angel Vermeer, Brandon Woolding, and Spencer Hill. And yeah, okay, so first some extrinsic motivation about why we study the tropics. Just from a pure human impacts perspective, more people live in the tropics than outside, so what happens in the tropics can have huge impacts. For instance, in countries like India, which are large agrarian economies, the livelihood is intimately tied to variability in the weather. And for instance, here's an image of my hometown, Chennai, which is under severe flooding in the winter of 2015, and the same region, in South India, was also reporting a historic drought by the summer of 2016. So less than a year experiencing both extremes, and obviously to understand extremes of rainfall or lack thereof, we need to understand tropical convection. But convection is not an isolated problem. Clouds are coupled to the circulation, and so we need to understand convectively coupled entities, and these convectively coupled entities span a wide range of spatial scales, going all the way from, say, a few tens of kilometers on the scale of a single deep convective cloud to all the way up to the scale of the ITCZ, which can span thousands of kilometers. Of course, they perform different functions and different scales, whether it be extremes of rainfall on a small scale or transporting energy away from the equator on the largest scales. It's important to understand convection and circulation as a holistic problem. And that's what I'll attempt to do in this talk. So it's broadly divided into two halves. The first half will talk about deep convection in the smallest scales, that is relating convection to its thermodynamic environment. And in the second half, I'll talk about some of the consequences of how deep convection operates in the smallest scales for dynamics of the ITCZ. Specifically, I'll talk about why we expect the ITCZ to narrow and intensify under global warming, and also touch upon some velocity profiles in the ITCZ, specifically differences between the East Pacific and the West Pacific ITCZ. Okay, so moving on to topic one. So convection is a complex problem with many processes such as radiation, downdrafts, cold pools, and entrainment, so on, operating at fast time scales and small spatial scales. And but we do need to model their effects in our global climate models. So the way this is usually done is to take these complex physics and compress them into a few simple parameters, or it's called the convective parameterization process. And at its core, a convective parameterization is just a function that takes information about humidity and temperature and converts this into information about precipitation or heating or whatever else you need to drive the model forward in time. And if you open up a convective parameterization, you often find a simple clown model that tries to do a lot of this physics in a very idealized way. Of course, nowadays, people replace the cloud model with a neural network, which gives you better performance, but not a lot of physical insight. But anyway, but there are parameters that come upon in this process that impact climate models in very obvious ways, and one of these is the entrainment parameter. So entrainment refers to the mixing between cloudy and non-cloudy air. And in reality, this is a highly complex process, but in models, it's a single parameter. And this slide shows you how sensitive some of our state-of-the-art climate models are to entrainment. So on the top left is the precipitation variance in the intra-seasonal time range from observations. And these two panels here in the bottom row show two instances of GFDL's AM2 model with two different entrainment values. So when your entrainment is low, your precipitation variance matches what you see in observations, but as you turn up the entrainment, you get excessive precipitation variance relative to observations. And the sensitivity to entrainment existed in the previous generation of the GFDL model, but this is also true for AM4, which is GFDL submission to CM6, or CM6, excuse me. And this figure shows that as your entrainment goes up or down, your precipitation variance can also go up or down. And what's true for the precipitation variability is also true for the mean precipitation structure. So the figure on the left shows you have the precipitation anomaly from the global mean changes as a function of the entrainment. And the point of this figure is to show that as you tune your entrainment, both the properties of the mean precipitation and the variability can change substantially. So our take was to try and constrain some aspects of convection, such as entrainment, using a combination of large data sets and some insights about how we think convection works. And the large data set in question here is data from satellites. So the TRIM satellite, over its lifetime, produced nearly 15 years of tropical rainfall measurements, giving you nearly 10 billion data points. And so that's like one constraint on some of the physics here. And the other constraint is what we think is it represents the essence of tropical convection. And the goal is to take all this data and create a function that takes inputs which are specific humidity and temperature and height. So these are profiles that go into the function, and we want an estimate of the precipitation. So in other words, we want to find precipitation P, which can be expressed as a function of temperature and humidity. So we want to do one version of the parameterization problem. And in this case, precipitation comes from satellites, specifically the TRIM effort, and the humidity and temperature profiles come from reanalysis, which is not exactly observations, but is at least constrained by it. And some version of this problem has already been done before. So we've known since the early 2000s that if you take, for instance, precipitation and a measure of specific humidity called column water vapor, which is just the vertical integral of specific humidity, and do a scatter plot, you get this relationship where in really dry environments, you don't have a lot of precipitation, but as you go to moist environments, you get pretty strong precipitation. And so if you want to relate precipitation to its thermodynamic environment, then P as a function of column water vapor is a pretty good candidate to start with. But notice also that there's a lot of scatter in the sense that each value of column water vapor corresponds to more than one value of precipitation. So what's usually done is to sort of sweep all the scatter under the carpet, which is done by taking small bins of water vapor along the x-axis and averaging all the precipitation that falls within a given bin. And when you do that, you get much nicer looking curves like these. So in the top right, you have precipitation now conditionally averaged by column water vapor. And this shows you this apparent threshold-like behavior where as you go from really dry columns towards moist columns, you hit this apparent threshold value of column water vapor, beyond which you get a strong precipitation increase. And the different colors here correspond to different values of column average temperature. And column average temperature, as the name suggests, this is the vertical average of temperature in the column. And what that tells you is that as your column gets warmer, the threshold water vapor value, which you have to hit to get precipitation going, also goes up. And if you shift these curves until they sit on top of each other or collapse, then you get this this candidate function that precipitation can be expressed as a function of both column water vapor and column average temperature. And this function actually works pretty well in a statistical sense, at least over tropical oceans. But even though it works well, it doesn't really help us understand the underlying physics of convection. So what we want is a physical model that can explain these statistics and also work better in other regimes aside from tropical oceans. And that's what we sought out to build. So what we want, so here on the right is tropical moist convection in all its complex glory. And this is too hard for us to model. This also includes the process of entrainment, so mixing between cloudy and non-cloudy air. So what we try to build is an idealized model of convection, here represented by this plume. In this case, smoke coming out of a smokestack. And this plume lives in the, so we'll assume in this idealized model of convection, we take the lower half of the troposphere, usually from the surface to about 5 kilometers, and divide this lower half into 2 layers. There's the boundary layer that's about 1 kilometer thick, and there's a lower free troposphere that's about 4 kilometers thick. And we'll assume that the plume, as it rises from the surface into the lower free troposphere, conserves a quantity called theta E, which stands for equivalent potential temperature, but this is a function of temperature and humidity that is conserved as you lift a parcel of air from the surface into the free troposphere. And this property is conserved except for one process in this model, and that's the process of entrainment. So as you bring in environmental air into the plume, you can change the theta E of the plume. And with that being said, I'll now define 2 sort of variants of theta E. The first one is theta sub EB, which stands for the average theta E in the boundary layer. The second one is theta sub EL with a superscript plus. This stands for this is a measure of the dryness in the lower free troposphere. So dryness being defined as the departure from saturation. So the further you are from saturation, the greater this theta E sub EL plus is going to be. Okay. So with that, if we know how much mass is being entrained laterally by the plume, we can say something about the theta E of the plume. But how much mass is being entrained, is of course the somewhat the thorny entrainment problem, which has long been unsolved. And our sort of take on the entrainment problem is to assume that the plume entrains a mass, unspecified mass, the lowercase a in the boundary layer, and an unspecified mass b in the lower free troposphere. So here a and b are unknowns, and the whole sort of the objective is to solve for both a and b. And the hypothesis, the working hypothesis, is that humidity and temperature don't directly give you precipitation, but they actually impact the buoyancy of the plume, which then impacts precipitation for the simple reason that convection, by definition, is driven by buoyancy. And we can show, using just like pen and paper, that the buoyancy of this plume at the top of the model is given by this expression. So it's got 4 terms. So A is the average mass entrained in the boundary layer, and theta sub EB is the theta E average over the boundary layer, and B is the mass entrained in the lower free troposphere, and this theta sub EL plus is just the subsaturation of the lower free troposphere. Okay, so with this expression, we'll now try and use the large data set that I mentioned before to try and estimate values for A and B. Cool. Okay, so this plot is now precipitation conditionally averaged by theta sub EL plus, or the LFT dryness. So notice that the x-axis goes from a positive value towards 0. So 0 dryness is just saturation. So as you head towards saturation, your precipitation increases in a non-linear fashion. But where this increase happens is also a function of the theta E of the boundary layer, which indicates the different curves here. So for instance, this blue curve, which has a large value of theta E in the boundary layer, shows a strong precipitation increase at about 15 units of saturation dryness in the lower free troposphere. But this red curve, which is a slightly less energetic boundary layer, so theta E in the boundary layer is slightly smaller, shows precipitation increase slightly closer to saturation. In other words, there's a compensation happening between the theta E of the boundary layer and the dryness of the lower free troposphere. And we can measure this compensation by simply shifting these curves until they sit on top of each other or collapse, and then plotting the degree to which you have to shift the curves along the theta EB axis against the dryness axis. And it turns out that this plot between these two axes is linear, and we can also show that the slope of this line is actually B over A. And recall that B and A are the unknowns of the problem that tell you something about the entrainment. And this is how we use the data to constrain the entrainment in this particular case. And once we constrain entrainment, we can go ahead and construct this new measure of buoyancy. This is called this is what we call the buoyancy averaged over the lower free troposphere, or B sub L, and it's given by this expression. So some of the terms in this expression you've already seen. So here theta sub EB is just the boundary layer theta E, and theta sub EL plus is just the subsaturation in the lower free troposphere. Now this theta sub EL star is the saturation theta E of the lower free troposphere. You can think of it as a measure of the temperature in the lower free troposphere. So together, this expression tells us that the first term is a measure of the instability of the lower free troposphere. It measures the boundary layer theta E and compares it to the saturation theta E of the lower free troposphere. And the second term is a measure of the dryness in the lower free troposphere, so the subsaturation term. And these coefficients, W sub B and W sub L of T, are functions of A and B, so they contain information about how much mass your plume is entraining. So together, this expression tells us that the average buoyancy of your plume in the lower free troposphere goes up when your instability goes up. But because this negative sign tells you that there's also a penalty you pay for operating in a dry lower free troposphere. So the greater your dryness, the smaller your buoyancy. And W sub B and W sub LFT tell you something about how much mass is entrained, and in doing so, they tell you the impact of the dryness on the lower tropospheric buoyancy. So we can derive all of this from data and some simple expressions. So what can we do with this? So the first thing, recall that I said over tropical oceans, if you just have column water vapor and column average temperature, the statistics for different tropical ocean regions look the same. Well, the same is not true for tropical land regions. So here we can see precipitation, conditionally averaged by column water vapor, and each panel on this figure is also controlled for by a value of column average temperature, and the different colored regions tell you are the different tropical land regions. And you can see that despite controlling for column water vapor and column average temperature, these curves don't really collapse as neatly as they do over the tropical oceans. In fact, the tropical ocean and land disagree with each other, and even the different tropical land regions disagree amongst each other. But if you do the same plot using buoyancy, you get firstly the strong degree of collapse over the four different tropical ocean regions. So you go from a non-precipitating region to a precipitating regime quite suddenly and strikingly. And the different tropical land regions that were in disagreement previously are in better agreement when you use this measure of lower tropospheric buoyancy. And in this sense, the claim is that buoyancy is an improved precipitation estimator for the tropics, at least compared to column water vapor and just column average temperature. So over the years, we've done a number of things, applied this buoyancy framework in several ways. Now let's talk about two particular ways. The first one is application to models, or diagnosing how models do in this measure. So I recall that precipitation is a function of buoyancy, and buoyancy can be expressed as a sum of this instability and the dryness metrics. And so instead of looking at precipitation buoyancy curves in 1D, we can look at a two-dimensional precipitation surface that's a function of both dryness and the instability metrics. And here you can see that this strong increase in precipitation along the z-axis as you head towards saturation, or if you make your instability greater in the low free troposphere. And you can use this plot to measure the sensitivity of precipitation to the low free troposphere, and specifically the sensitivity of precipitation to moisture in the low free troposphere, and express that sensitivity as an angle, and that's what is shown here, and that's the angle that this orange vector makes with this dryness axis. And in this case, this angle is close to 45 degrees, and the physical interpretation is that precipitation in this data set is about equally sensitive to both the dryness and the instability. And this data set was constructed using TRIM 3D42 over the oceans, and also this specific humidity and temperature profiles came from ERA 5. So we can take this as our observational baseline and then ask how different climate models do. So here I'm showing the precipitation surface as a function of dryness and instability for two specific models. And you can already visually see that these two models are quite different. So this model on the left has a precipitation sensitivity that's pretty close to the observed baseline. You can tell that from the angle that we computed. But this model on the right has a precipitation surface that's too far along the dryness axis. In other words, this precipitation in this model is oversensitive to water vapor in the lower free troposphere and not sensitive enough to the instability. So we did this for multiple CMIP6 models, and this polar plot is sort of a depiction of the moisture sensitivity of all the models we analyzed. So recall that the angle is a measure of the moisture sensitivity of precipitation in each of these models, and an angle close to 45 degrees is close to observed. So in this plot, the two gray dashed lines tell you the range of observed uncertainty. So they're close to 40 degrees. And each of the colored dots, the markers, tell you the precipitation sensitivity of each model we analyzed. So the good news is that most of the models we analyzed sit within the observed uncertainty range, which is good news, suggesting that most modern day climate models have about the right sensitivity of precipitation to moisture in the low free troposphere. So a handful of models, although do have inadequate sensitivity to water vapor in the low free troposphere, they have this moisture sensitivity angle that's much higher, at least when compared to the observed uncertainty range. And but we also identified a subset of models shown here in this gray shaded area, where the models are oversensitive to the low free tropospheric water vapor. So these models have angles too close to zero. And to try and explain why these CMIP6 models exhibit this spread, we took a single atmospheric model, CAM5, and simply played around with its entrainment rate. So when your entrainment was too low, we found that these models, the CAM5 models showed a moisture sensitivity that was also too low, comparable to this set of models here. And when the entrainment was at its control value, CAM5 sort of sat within the observed uncertainty range. And as you turn up the entrainment, the moisture sensitivity of CAM5 continued to increase. And when you took away the convective scheme entirely, so this is the limit of infinite entrainment, CAM5 sort of sat in this range where the model was too oversensitive to low free tropospheric moisture. So this is sort of an illustration how we can use a combination of process level insights about convection and perturbation experiments with climate models to try and constrain some of these highly sensitive and uncertain parameters in complex climate models. And this sort of diagnostics, if you're interested, is available as a part of this diagnostics package, which is it's called the MBTF diagnostics package, which is developed and maintained by JFDL. Cool. So that was one sort of pragmatic application for model diagnostics. Here is another sort of unintended application that just came out. So this is a paper led by Suchin Duan, who was a colleague of mine and a scientist in the group. And in this paper, so take the non-entraining CAM5 experiment that I mentioned in the previous slide. And again, you have the dryness axis and the instability axis. And the green PDF here is a PDF of precipitating points, and the brown is the PDF of non-precipitating points. And notice that the range of instability values sampled in this world without entrainment is sort of bound very close to zero. And this is because as soon as you develop a little bit of instability, you produce convection in the model, which just eats up your instability. So, and it's also been shown, quite recently, that this instability can be used as a proxy for these so-called moist heat waves, which are really instances of high surface red bulb temperatures. So red bulb temperatures are more impactful for human health than simply measuring dry bulb temperatures. And it turns out that by this interpretation, convection actually limits the intensity of moist heat waves. But if you take a world with entrainment, like the one on the right, so this regime that was previously inaccessible to the model is now sort of opens up, and the model can sample sort of more points in this regime that has high instability, and this is because, as we saw previously, to attain the same amount of buoyancy in a world with entrainment, your instability has to go up to compensate for the dry air that you entrain. And so sort of the takeaway here is that a world with entrainment has more intense moist heat waves compared to a world without. And as the planet warms, the lower free tropospheric dryness is projected to increase. So this would also imply an increase in the intensity of moist heat waves. And if you're interested, this paper came out this year in Nature Geosciences. Okay, cool. So that sort of completes the first half of my talk, where I touch upon the physics of deep convection at the small scales. So I'll now sort of switch gears and move on to the dynamics of the ITCZ, the large scales. And before I move on, if you have any questions about this, feel free to ask. Yeah, go ahead.
Just a clarification question. Your plot that has buoyancy versus precipitation or curves out and they all converge essentially. There's a small sliver where you have negative buoyancy but also precipitation. So just for clarification, is that representing elevated buoyancy, or is it what does that represent in terms?
So that's something we note empirically, but we don't have a full understanding of. But a couple of hypotheses is that we are only using grid scale quantities to compute buoyancy, but perhaps convection is really triggered by like above average grid scale values of buoyancy, so it's not reflected. And secondly, if you have sort of triggers for convection that are not thermodynamic, like colliding core pools, for instance, then they wouldn't be reflected in this measure. So we haven't really solved, why do you not have onset at exactly zero buoyancy?
On your previous slide, you said that in a warming climate, you would have a drier free troposphere.
Mm-hmm.
It seems like it would be. I mean, you're carrying in a warmer climate, you're carrying more water vapor.
Oh, yes. So
assume that it's a drier free troposphere.
So in a warmer climate, there's a whole wet gets wetter, dry gets drier paradigm.
Okay.
And I was thinking of subtropics that would get drier
Okay.
and more susceptible.
Thank you.
There's also a saturation deficit if the relative humidity stays the same.
Yeah, the relative humidity stayed the same, but
Then the saturation deficit increases.
yeah.
Okay, thanks. Thanks.
Yeah, so that's the deficit from saturation.
Okay, so moving on to some ITCZ dynamics. So ITCZ for this paper, I define as regions of the tropics that have time mean ascent, but also have strong climatological precipitation. And we know from mostly coupled model experiments, and also recently by observing trends over the historical period, that under global warming, the ITCZ gets narrower, but also gets more intense. And the simple question is why? And the why part of this question is, there's somewhat of an answer from a series of papers by Mike Bourne and Tapia Schneider, who compute the energy budget of the atmosphere, and they would essentially relate changes between the energy partitioning into the ITCZ to the changes in the ITCZ fractional area. So in other words, if you know where the ITCZ is, if you know how wide the ITCZ is, you compute how much energy goes into an atmospheric column within the ITCZ, and if you perturb the energy that goes into the ITCZ, you can relate those perturbations to perturbations in the width of the ITCZ. So this is an existing area. It's sort of it's an area for the change, and it's very powerful and useful. But we want to sort of go beyond and try and ask a more a basic question. That is, given an SSD profile like this, can you say something about what a world throws with an SSD profile like this? What is the resulting precipitation profile? And this is, of course, a hard problem to do in a fully complex GCM, but if you simplify the problem enough, you can do this problem analytically. And that's what I sort of set out to do. So basically express ITCZ area as a function of the surface temperature and a bunch of other parameters. And to do this, we can leverage the fact that in the tropics, column water vapor, at least over the time mean, column water vapor separates the tropics into a dry, non-precipitating region and a moist, precipitating region. And you can sort of see that. This is a plot of the average climatological rainfall from GPCP over 21 years. And this white contour is a single contour of column water vapor from era 5. And you can see that this single contour almost perfectly delineates the regions that you would intuitively think of as the ITCZ. So if you want to say something about the ITCZ area, you can use the fact that there's a moist area that sort of bounds the ITCZ area. So in other words, given a profile of SSD like this, you can first derive a moist area like the one in orange, and use that to then derive a precipitating area, which for our purposes is just the ITCZ. And once you have an expression for the precipitating area, you can then measure the width of the precipitating area and say something about the ITCZ width, albeit in this idealized framework. And to do this, again, we took a simple model where we prescribed the shape of the SSD profile, and this model has no rotation. And if you're familiar with the literature, this sort of follows a class of models called the mock overturning circulation class of models. So no rotation, and you have one overturning circulation that arises in response to a prescribed force. Okay, even though the model is simple, we still have to put in some physics. And I specifically put in physical information about radiation. So we have clear sky radiation, cloudy sky radiation, and convection. And all of these are parameterized as functions of either the column water vapor, Q, or precipitation, which depends on the column water vapor. So these are all directly or indirectly functions of the column water vapor. And you also have information about the poleward export of water vapor. And this is parameterized on the surface temperature itself. So the Laplacian of the surface temperature tells you something about how much you export out of the model at the edges of the domain. And all of these parameterizations, we use data from climate models where we fit curves, for instance, here between clear sky radiative heating and column water vapor, here between OLR anomalies and precipitation anomalies, and here between precipitation and column relative humidity. And okay, so that's the physics portion. And then we can go ahead and in this simple model derive this atmospheric energy budget, and similar to the Bohr and Schneider framework, and you end up with this innocuous looking expression. So on the left hand side you have a parameter called the gross moist stability. You might have heard of it. It's sort of a parameter of some notoriety in tropical dynamics. That's very important, but also very hard to measure. There's a lot of interpretations, but so the one that I'm going with is that it measures the efficiency with which convection exports moist static energy out of the column. And on the right-hand side, you have some terms. This includes information about clear and cloudy sky, radiation, evaporation from the surface, and also precipitation. And into this expression, we can throw all of the physical parameterizations for convection and radiation, and also our functional forms for surface temperature and column water vapor. And you can solve, and what we get is this quadratic expression, where the unknown is this y sub p, and y sub p is the width of the precipitating region, or the ITCZ area in this model. And these coefficients of the quadratic are actually functions of all the physical parameterizations. So once you solve for this explicitly, we can then ask how the model does in response to, for instance, SST changes. So here on the left, I'm forcing the model with different values or different profiles of SST. Here, the spatial dependence of the SST is exactly the same. It is simply being changed by 1 Kelvin increment or decrement uniformly. So in response to uniform SST changes, you can see that the shape of the resulting precipitating area is not the same. So when the SST is weaker, you get this wider, weaker ITCZ, but as your SST gets stronger, uniformly, your precipitating area of the ITCZ also gets narrower and more intense. And we can also measure the strength of the ascent and the descent, and we find that the ascent gets stronger as your temperature goes up, whereas your descent gets weaker. This sort of follows observations, at least observations over the historical period. And the claim is that over the, so this very simple model can capture the leading order behavior that you see under global warming. And even though the model is simple, it does have some explanatory power when it comes to diagnosing climate models. So we analyzed about 29 AMIP models, and essentially we computed the change in the ascent area, or the ITCZ area, over the historical period, expressed in units of percent per K. Here, that's on the x-axis. And on the y-axis, you have a prediction for the ascent area change that comes from the very simple model. When the simple model is forced with parameters corresponding to each of the different AMIP models. And the point here is that the simple model prediction has this relationship to the AMIP models that you actually observe, and you'll note that the relationship is not perfect, but you can explain some portion of the intermodal spread using the simple model, and upon digging deeper, we find that the gross moist stability term that I sort of alluded to previously explains most of the intermodal spread in this cohort. Okay, so this is sort of the last section of my talk. I'm going to talk about vertical velocity profiles in the ITCZ, and specifically asking why the vertical velocity or the omega profiles look different between the East and West Pacific ITCZs. Okay, so we've known for a long time, thanks to work by Larissa Back and her collaborators, that if you take a region in the East Pacific ITCZ and in a region in the West Pacific ITCZ and look at their vertical velocity profiles, they look quite different. For the E-specific ITCZ, the omega profiles have a single maximum in the lower troposphere close to the boundary layer, so these are called bottom-heavy profiles, whereas those from the West-Pacific have a maximum in the upper troposphere, so these are called top-heavy profiles. And even when you control or for the amount of precipitation, these differences persist. So, and these show up in composite analysis, but they also show up in, say, statistical analysis. So here are EOFs of vertical velocity profiles from reanalyses, and the top two EOFs are the deep mode in black and the shallow mode in red. And these explain a bulk of the variance in the precipitating tropics. And if you project these EOFs onto raw vertical velocity profiles, you can construct these top heaviness ratios that tells you that these bottom heavy profiles are mostly confined to the East-Pacific ITCZ and maybe a little bit to the Atlantic, whereas the top heavy profiles are found in the warm pool of the Western Pacific and the Indian Ocean. And the question is, why do these differences exist? And there are sort of prevailing theories or ideas, and one of them is that when your convection is forced by buoyancy, where you warm the boundary layer or cool the low free troposphere or moisten the column, that convection tends to be top heavy. But when your convection is instead forced by strong convergence of mass into the boundary layer, that excites convection. The resulting convection is more bottom heavy. And over the West Pacific, where you have warm waters but weak surface convergence, you tend to see this top-heavy mode, but over the East Pacific, where you have strong meridional gradients of the SST, you tend to see this bottom-heavy mode. So the idea is to try and explain these sort of features more quantitatively. And to do this, I'm sort of going to do what I did before, that is try and build a model that can reproduce some of this behavior. And the model in this question is slightly more complicated. It's a model that is steady, so there's no time variations, but it's got layers in the vertical. More specifically, it's got n atmospheric layers. Okay? And it's forced from the surface, either by with both a surface temperature and a surface-specific humidity forcing. And the layer closest to the surface, I'll call it the boundary layer. The layer at the top of the atmosphere, it's just the outer troposphere. And you have these indices going from 0 to n-1, so n layers. And within each layer, there are these variables. So T is the temperature, delta is the horizontal divergence, and Q is the specific humidity. And this model has a uniform background state. So there's a background state that is not varying in space, and also rotating on an F-plane, so the rotation rate is the same everywhere. And these variables, T, delta, and Q, are actually linear perturbations around this uniform backgrounds. And so we have unknowns, or more specifically, we have 3 times n unknowns, so 3 unknowns in each layer, and we want to solve for these unknowns. Okay. And to do that, we need some physical constraints. So these are my constraints. So I have these momentum equations that relate the horizontal divergence to temperature, and the momentum equations contain information about friction and rotation rate and so on. But also within each layer, I have thermodynamic equations. Specifically, I have a thermodynamic equation for temperature and another one for specific humidity. For instance, this pair of thermodynamic equations in the boundary layer is a balance between adiabatic cooling or moistening versus sources of sinks of dry static energy or humidity from the surface, and then the action of convection. So convection can either heat or cool your column, it can also dry your column, and you can also have radiation that can heat or cool your column. And you can write these equations for each layer. So the takeaway here is that you have 3 n unknowns, you also have equal number of constraints, so you can solve this. But to solve it, you need to sort of specify the action of convection and radiation in terms of the unknowns, and also preferably linearize it. And the closure for convection of radiation is given by this expression. So here I have the Q on the left-hand side is a column of either convective heating, drying, or radiative heating. And the T and the Q are columns of temperature and specific humidity. And these M's here are simply matrices. And so the physical interpretation here is that given a column of temperature perturbations and a column of water vapor perturbations, I have these matrices that transform them into perturbations of either convective heating, drying, or radiative heating. And if you are familiar with the literature, these are essentially the linear response functions from Jimmy-Kwan. Okay, so just stepping back, I have this M-layer model, and I find a way to linearize it using a variety of methods. Then I make this assumption that all my perturbations are varying exponentially in space, and and then there's this k there that gives me a length scale. Okay, so that's my model, and once you've linearized it, you can solve. You can use methods to solve linear systems, basically. And the first thing you can do is solve for these so-called free modes, or eigenmodes, or internal modes. And I'm showing results for n equal to 4, so 4 layers. And you can do this by setting the surface temperature to 0. So in the absence of any external forcing, what are the model physics tell you? So you get many modes. Specifically, you get 2 times the number of layers, so you get 8 modes in this case. But I'm only showing you the 2 modes with the 2 largest spatial scales. So the red mode is the deep mode, and the blue one is the shallow mode. The red mode has a spatial scale of about 1,500 kilometers in this case, and the shallow mode has a spatial scale of about 250 kilometers. And you'll notice that these 2 modes correspond to these shallow and deep EOFs that you see from observations. And each of these 2 modes also have specific shapes of temperature perturbations that they go along with. The deep mode has a deep temperature perturbation, whereas the shallow mode has the shallow temperature perturbations. And the takeaway here is that the deep and shallow profiles are actually physical modes of the system, and they sort of exist they show up in the data for a reason because they satisfy the governing equations. Okay, so this is the unforced problem. You can then take the same model and force it with an SST profile. Actually, before I go ahead, recall that I told you that you have 8 modes, but I only showed you 2. There are actually other higher order modes that are shown here in gray. These higher order modes actually have much smaller spatial scales than the blue and the red modes, so they end up not contributing to the solution as much. So these do exist in the equations, but they don't emerge in nature because of other constraints. Okay, so the first problem. So here, I'm now solving the same 4-layer model with a 1 Kelvin SST forcing. And I'm doing this for 2 cases. One is where I have a strong SST forcing, where your SST goes from 1 Kelvin to about 0 over a distance of 250 kilometers. And then I have a weak SST gradient, where the SST goes from 1 to 0 over a distance of 2,000 kilometers. And the strong SST gradient case is also slightly off the equator, and the weak SST gradient case is slightly closer to the equator. So these are meant to mimic conditions in the East Pacific and West Pacific. Okay, and this is what I forced the model with, and this is what the model prediction is for precipitation and temperature. So first thing to note, the red is a precipitation that the model predicts, and you'll know that the model precipitation doesn't exactly follow the SST forcing. They're not the same. And on the right, I have predictions for temperatures. The blue is the boundary layer temperature, and the orange is the upper tropospheric temperature. And when the SST gradient is really strong, your boundary layer temperature gradients are also strong. But your upper tropospheric temperature gradients are not actually following the same shape. They are set by different physics. And as you get away from the convective zone, that is as you move rightward of the dashed vertical line, you'll notice that your temperature drops really slowly. So this is sort of telling you that you have really weak temperature gradients, mostly in the tropics, And if you sort of ask why you get these weak gradients, it's because you have this deep mode that I introduced before that has a really large spatial scale and carries information from your convective zone over vast distances and therefore sets this weak temperature gradient, or WTG, over across the tropics. Okay, and for the same problem, you can also ask what the vertical velocity profiles look like. So here the blue is ascent, and the faint red, which I think is showing up as white, is descent. So you have a region of strong ascent and a region of weak descent in both cases. And these profiles are simply profiles along transects in the convective region and a little bit in the non-convective region. So basically, when your SST gradient is really strong, you get these bottom-heavy vertical velocity profiles. And when your SST gradient is weak and you're slightly closer to the equator, you get these top-heavy vertical velocity profiles from the same model. And the claim is that this sort of reproduces the behavior or the differences you see in reanalysis between the East and West Pacific ITCZs.
What are the colors, did you say again? The different colors of the omega profiles?
So,
Those are different latitudes or
So these are,
different locations in the domain?
Yes, as you move from 0 into, let's say, 500 kilometers, I'm simply taking transects
Okay.
along different points of the x-axis. And the most intense vertical velocity profile is at x equals 0, and as you cross over into the non-precipitating zone, you sort of get the more yellowish ones, which are kind of weak on this.
Okay, thank you.
Yeah. Anyways, yeah, so that actually brings me to the end of the talk. And this is so the first half I showed how tropical precipitation can be related to its thermodynamic environment using a combination of data and simple physics. And the second half I showed how we can use simple models to understand some of the dynamics of the ITCZ, specifically why the ITCZ narrows under global warming, and why you see these top and bottom heavy vertical velocity profiles in the East and West Pacific ITCZs. Okay, so I'll end there and yeah, take questions. Thank you.
I think we usually ask for student questions first, so maybe there's some, are there any student questions? No student questions? Any other questions? I have questions, but I'm gonna wait. Yeah, Liz.
Silence. This is really cool, like all of this. Nice to see things I didn't know about in a while. So in the tropics, there's this big double ITC bias in climate models. So when you're talking about the narrowing of the ITCZ, I saw you doing most of the AMIP simulations. Does this double ITC bias, when you move on to fully coupled simulations, make a difference in how you interpret ITCZ narrowing? Does it mess with these kind of interpretations?
It does. Okay, so the reason I use AMIP simulations is because I'm asking if a model, if you have two different models that are forced to the same SST profile, why they give you different answers. So that's the problem I'm after. So that's why I use AMIP simulations. And but when it comes to double ITCZs, the ITCZ area is defined as the area of the ascent. So you take it's in 2D, and it's sort of agnostic to the pattern of the precipitation. So you simply take all the grid points that are ascending, and then you add them all up. So that definition is somewhat, it's agnostic to whether you have a single ITCZ or a double ITCZ. But the same analysis with single models is not as good. And that's because the SST patterns are different.
When you say different, you mean like in the zonal direction or in like the vertical direction because of ITCZ?
I mean, I would guess in the meridional direction. I haven't done a detailed sort of parsing of each direction, but yeah, that's my guess.
The last part, you're looking at the different top versus bottom heavy profile based on the curvature or the precipitation set of the SEC there. If you look at ENSO versus like El Niños versus La Niñas, where you're able to like maybe get those differences in observations, do you see those same variations in observations as you see in the model here? Does that coincide with that?
So are you asking if the top heaviness sort of varies as a function of ENSO?
Yeah.
That's an analysis I've done. Have you-
Miguel did that. I think Miguel showed you that it does.
Yeah, but it's consistent with the simple model here.
Oh, with this simple
Does-
model.
Does ENSO impact
Does the,
myriad
I think
of-
he's asking, would the simple model reproduce what you see with ENSO?
Oh, the simple model is simply,
And you haven't looked at that.
no, it's only sensitive, so this analysis is only sensitive to two things, the gradient of the SSD and the latitude. So if the ENSO variability impacts those parameters, then you could reproduce it. And,
If that's the mechanism
Yeah,
via
exactly,
which
yeah.
ENSO is influencing the top
yeah,
heaviness.
exactly, yeah. Yeah.
I have a naive question, I don't know the tropical stuff. What, in this last example, what is the response on SST from the precipitation itself? Is it reorganizing the gradient? Does it act to intensify the gradient, or does the cooling of it actually reduce the gradient such that it's, you actually see a reduced response in time?
Yeah, I mean, yeah, that's a good question. So in this problem, the SSD is externally specified, so it's not impacted by the precipitation. But you could do a version, for instance, with a mixed layer at the bottom, where it gives you an SSD prediction, and the SSD is interacting with the atmosphere. But then you'll need to specify the forcing from the deep ocean. So this is,
And then the precipitation would reduce the gradients.
yeah.
That's, yeah. So I have a question about, can you kind of talk about the physical interpretation a little bit of the bottom heavy case being associated with strong meridional SST gradients and the top heavy case being associated with weaker meridional SST gradients, like why that happens? Not this well,
Yeah,
because
yeah,
it's on this one, but yeah.
So that's something I'm still mulling over, but the answer I have right now is that the gradient of the SST sets the temperature structure. So basically, it sort of sets the deep versus shallow temperature structure, and which then necessitates a deep mode or a shallow mode. Now I'm not clear how it sets the temperature structure. This is just a back of the envelope analysis of the simple model that I'm still working through. Yeah.
Okay.
It's not super clear yet.
Okay. Thank you. Other questions or? No? Okay. Let's thank Fiaz for a great talk.